I'm going to demonstrate Gumshoe, a tool to identify exactly what parts of a Java application are generating all your network traffic. The Gumshoe probe writes periodic samples to a text file that include the call stacks and how much network I/O those stacks were performing. You would then use the Gumshoe viewer to understand the network utilization associated with individual lines of code in your application. Without the right visualization, this can be overwhelming, especially with a complicated dataset. So let's start with a much simpler example to understand how to use the viewer to filter our dataset. Let's begin with this very simple Gumshoe data file. I've created this one by hand just as an example so we can see some of the features of the viewer. There's 4 call stacks all within one sample. Each call stack is marked with the network operation statistics. The sample has a beginning and an ending tag, and a typical data file will probably have more than one of these samples written out at regular intervals by the Gumshoe probe. Let's take a look at that data file now in the Gumshoe viewer. Each of the 4 call stacks is a column in the display. I can see that this is currently set to the flame graph view, which is going to group the calling frame at the bottom of the call stack, in this case thread.run if it's the same. So in the display I have 3 call stacks that share this initial frame, and the statistic shown for this cell, the thread.run call, is going to combine the statistics of the 3 call stacks that share it. The other common view for the viewer is to show a root graph, which is the same call stack information grouped at the other end. Now, instead of the initial point of entry into the call stack, I'm looking at the other end where it's the call stack calling out to the read or write operation. Here I'm grouping together the 2 frames that do the socket input stream read, and in the other 2 stacks I'm grouping the frames that do socket output stream.write. Again, the statistics shown for that cell is the combination of the statistics of the 2 call stacks. So far we've had cell width set to equal width, which gives no real indication of the relative network load of each of the call stacks that I'm viewing. What I probably want to do is view statistic value and scale the cell width by that. If I make that change, I can see here in this graph that this particular call stack is responsible for a good portion of the I/O load that's occurring right now. At the moment, I'm measuring read plus write number of operations. So I have a little more than half by this call stack, a very small amount in this call stack, a little less than half here in this 3rd call stack, and a very small amount in the 4th call stack. If I change the measurement to bytes, I can see that one of the 4 call stacks is responsible for the bulk of the actual size of the I/O operations, but a different call stack was responsible for the majority of the number of operations. So this call stack did a lot of small I/O, and this one did fewer large I/O operations. Okay, so far so good. If your application only has 4 possible paths through code and 4 call stacks that perform network I/O, maybe call stacks that are only 6 or 7 frames deep, then we're probably good to go. To look at network utilization in a more realistic application, we're going to have to go back and think a little more about the call stacks. If we're looking at a real production application, we're going to have a much bigger call stack, and we're going to have a lot more paths through your code that perform socket operations. A typical call stack in the application that I'm monitoring is going to have dozens to over 100 frames. It's going to start at the very bottom with some JDK calls like thread.run, work up through the third-party REST utilities that we're using, through some session interceptors and things like that that are sort of general utility classes, both within our application and third-party libraries, and then get into the meat of the application where we have the operation itself being performed, the business logic that that's going to call, and then have it manipulate the various domain objects. Those manipulations are going to pass up through additional utilities and wrappers, and then through whatever kind of drivers, maybe JDBC or some external REST call, and then finally up through the JDK again, where it does the HTTP or the socket operations until it finally gets to a socket.read or write. One of the important features of Gumshoe is the ability to apply stack filters and limit the analysis that you're performing to just those portions of the call stack that are relevant to your current investigation. Let's return to the more complicated example we saw earlier and see what we can do to remove some of the noise from this image. We have very tall call stacks, each representing, in a lot of cases, not a whole lot of I/O. Some of the groupings we have here are things that are not relevant to my investigation, the Gumshoe collection itself, things from the JDK. So I'll go to Filter. As a bare minimum, you'll probably want to apply this filter, which is to drop things from the JDK and Gumshoe itself. I'm going to go a little further and limit this to just packages that are part of my application. And back in that original image, we saw there were some things that were kind of framework and interceptor type of things. I'm going to exclude those specifically. And that should drastically reduce the number of frames that I'm looking at. Now I see much smaller call stacks, much more relevant frames. If I go over to display, I can arrange by value, get the things with the most utilization on the left, see the top contenders here for things that are calling out to various services and using a lot of network operations. I can also get rid of all of these on the right side that are a whole lot of different call stacks, but each not contributing much to the overall load. Let's drop everything that's less than, say, 1%. Now I have many fewer call stacks shown, a lot more relevant information, a lot of the noise has been removed. I can see right across the top exactly where my application is calling out and using a lot of network resources. Within the same target application, the same filters will make sense over time. So I could go back to my data file and move to the next sample in the file. Now I'm looking at a later 10-minute interval in the dump file. I can also change to the flame graph. With the same filters, I can now see what the differences are in the invoking call. So I'm getting into this application, in this case, through a REST call. In this case, I'm looking at the load generated by some asynchronous tasks that had been submitted to the system. That wraps up my presentation. I hope you try Gumshoe. I hope it's useful and solves all of your issues with network performance. Give it a try and let me know what you think.